So this is a second video I'm doing that is related to divergent sequences, where I initially got into this because I was trying to replace uses of infinity with recursion, and especially eliminating infinite processes. So just as kind of a refresher, if you haven't seen the previous video, there are some sequences that come out looking ridiculous in spite of the fact that you've done nothing unusual at all. If you are just mechanically doing algebra and you take a equals b to mean that if you see an a, you can replace it with b, and if you see a b, you can replace it with a. Just like all the basic arithmetic that you're used to. The only real caveat being that you can't divide by zero. You can't say that one integer is equal to a different integer. Finite integers, at least. So you're just doing like really, really regular math. Like this is something I ran into when I was trying to automate mathematics on a computer. You have to deal with this. Divergent sequences and sequences that don't diverge. And so I guess the first thing we're going to talk about is an instance that that if I can't convince you that there's nothing wrong with this sequence, you're not going to believe the next one at all, because it's even though it's similar in a lot of ways, it's just way more complicated. But this is probably the easiest one to understand. So if you have a sequence, let me find my mouse. Where the hell is my mouse? There it is. Okay, so if you have a sequence like 1 plus 2 plus 4 plus 8 plus 16, there is a way to derive that sequence through recursion, which basically just means that you happen to have a variable on both sides, and of course that happens all the time. If it didn't, you wouldn't be doing dividing out a variable. In any case, say that we simply want to give s a name and just call it -1. So all that we're saying is when we encounter s later, we know that it's equal to -1, right? And so if we multiply s times -1, we got minus s is equal to 1. And we can expand that out to 1 minus 2 times s is equal to 1. And then what we can do is we can distribute s across them, s minus 2s equals 1, and then we say s equals 1 plus 2s. So what we're saying is, literally we're saying that -1 is equal to 1 plus 2s. And I'll show that that's actually the thing that makes the most sense. There's another phenomenon that says if you have a sequence that would otherwise be an infinite sequence, this is a common thing. So if you want to get the first n terms, you could have an explicit formula for the first n terms. And so you have this value that the sum sort of is, it's the sum is not actually equal to the value s unless the tail goes to 0 when n gets large, right? So if you want to say s is equal to sum s of n, as n gets large, this thing better go to 0. And this is where most people like get lost when they're thinking about divergence and they don't believe this stuff. So in any case, if we know that s is equal to 1 plus 2s, we can just keep substituting it in mechanically, exactly like a computer does. So you do s is equal to 1 plus 2, and then you substitute in 1 plus 2s. And then you go to simplify things, and you say 1 plus 2 plus 4s. Right? That's one substitution in. And then again, we go through and we see an s and we replace it with 1 plus 2s, and then we flatten it out, so 1 plus 2 plus 4s. And do this again. After we go up to 16s, and then we notice we got a pattern. So it's 2 to the 0 to the 1 all the way up to 2 to the n. And then where this really comes into being something possibly different from what you've seen before. When you have your first n terms summed up, you absolutely can't say plus ... You have to specify what the procedure is, otherwise it's like nonsense. It's nonsense, not in a sense that I don't know what you mean, but it's nonsense in that you haven't given me a procedure that I can actually implement in code. Like, I need a procedure. If you say plus dot dot dot, you need to tell me like how that happens. In this case, you add up 2 to 0 to the 1 all the way up to the n, and then you know that thereafter it's going to be 2 to the n plus 1 times s. You notice in this case it's s times something that's over here. So as this gets large, the value of s would get large, but in order to have its value, this tail also is added on the other side. So you got to be careful when you say that 2 0 2 1 2 2 plus dot dot dot. That's like a half-written statement. You say it quote unquote goes to infinity, but the problem is there are many numbers with an infinite number of digits that don't have the same value. Like infinite number of 9s going out to infinity, or infinite number of 7s. They're infinite values. One is not larger or greater than the other. That's the crazy thing, because they have an infinite number of digits. So they're not comparable, yet they're both quote unquote infinity, but they're values that are not equal to each other. So you got to get away from just like being lazy and saying, the limit goes to infinity, but that's not really that's not really a notion that we're doing here if we want to be able to actually like calculate things concretely. Okay, so in any case, we have s. I expanded it like this, and I came up with this equation, and I literally only started from s equal to -1. And so if I really believe that s is equal to -1, then I put -1 over here and say 1 plus 2 times -1. And is this minus 1? Yes, it is minus 1, right? Because it's 1 minus 2. And this would be 3 minus 4, so that's minus 1. And this would be 7 minus 8. That's also minus 1. So what it means is every time I expand it, the sequence gets longer and larger, but this value on the other side does not change. And that's basically like what this is all about. So if you expand a sequence, quote unquote, to infinity, if you expand it, quote unquote, forever, the value never changes whether you represent it as this full thing or you represent it with fewer terms, right? You say you get tired after you've written 4 or 5 terms, and you just want to write it like this. You don't do plus dot dot dot. What you do is you continue to the next one, and then you multiply times s in this case, and that will give you something that, because it uses recursion, it does expand infinitely, but it is absolutely mechanical, and you can calculate everything that you need to calculate. And maybe you didn't realize there's some things that you need to be able to calculate to do this correctly. So I'm going to tackle -1/12 is equal to the sum of all integers. I didn't do it in the first video because it's a way more complicated sequence. What I just did here is I did the -1 equals the sum of all powers of 2, and you see exactly this in computers. If you flip all the bits, turn all the bits on, if you add 1 to that, you get 0. That's why it's called -1. Right? There's a good reason for it. Okay, so in this case, I don't even want to write down what I usually see where I say -12th is equal to this, because that plus on the end is a problem. It's the cause of everybody on the internet arguing, even real mathematicians arguing, which blows my mind, like there isn't one mathematics. But this is related to P-Adic numbers, but the thing is P-Adic numbers aren't like a weird number system. They're just a result of like doing the algebra and taking the equality operator seriously. Like if I say s is equal to 1 plus 2s, I can't avoid solving s for -1. There's nothing I can do about it, and I also can't avoid expanding it to sum of all powers of 2. That's just how it works. So if it fits the pattern, you don't need to use altered weird versions of the number system to make any of this stuff work. You just need a different mindset where you don't waffle your way through and say that's ridiculous because you don't like the result. Because the problem is you start from axioms, you apply rules, and you can't object to any of the results that you end up with because they came from the axiom where rules were applied to it. So if you don't like where you ended up, you have to change the rule, or you have to change an axiom. Just like you're writing a code, like you can't, you give it input, you run the program, and if you don't like what the program does, you have to change the program, or you have to change the input. You can't just object to what it did. Okay, so here is a sequence: 1 plus 2 plus 2 plus 5 plus 5 up to n. And then we add in the tail to represent all the other stuff that we didn't write down. And the reason why that's there is it's needed in order to calculate this thing out to infinity, so that whether I expand it a small number of times or a very large number of times, s is always the exact same value, right? So if I expand, if I say 1 plus 2 plus tail s of 2, what I'm doing is saying I got tired and I didn't want to write everything after 2, and so I just put on tail. Most people will write it until it seems unambiguous, whether it's gonna be powers of 2 or it's gonna be linearly increasing numbers. Okay, and here it's a really common phenomenon. This stuff here in parenthesis is the sum for the sequence s expanded n times, and in this case, we have a tail that says that if it's been expanded n times, a tail is everything that hasn't been mentioned yet. And it happens to be that if you were to expand it twice as much, so instead of expanding 5 terms, I now expand 10 terms. Well, I get the tail for the sequence, after it's been expanded 10 times. So the interesting thing about 1 plus 2 plus 3 plus 4 plus 5, even though the infinite derivation is really, really hard and dastardly, it's not too hard for the finite case. For the finite case, most people already know that n times n plus 1 divided by 2 gives you 1 plus 2 plus 4, blah, 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 up to n, right? And it is actually related to this weird sequence. But in any case, I have number s, and instead of writing it out, 20 numbers and then tail s of 20, I can actually write it in its closed form. So this is the closed form for it. So the sequence n plus 1 over 2 plus its tail. If you think about it, we haven't constrained what s is at all. It's just some unknown value. It might be infinity. That's what you would expect, actually. But then when you start looking at I'm really being really specific, I'm not using plus ... and now I can't do that. So at least you know that if this is the closed form, then if you want to have the tail, well, if you know this or this, you can calculate s, right? So usually you either don't know the closed form or you don't know the tail, right? You use the other two to work it out. So if I have a closed form of n times n plus 1 and I have s on the other side, then this would be equal to s if I drop the closed form, right? So the tail actually ultimately has to be this. And you may not have enough information to nail down what s is. That's the tricky part about this sequence, figuring out what s is. And people get really surprised that it's negative 1/12. But it's actually not weird at all, because you can have an infinite number, like P-Adic numbers, where it's a lot like a finite field. Like in a finite field that's prime modulus, you could have some place where 13 is the inverse of 250, and something like that. And so it would literally be 1 over 13 is equal to 250, and maybe 250 is a large number in the system. Like, wow, how do you do that? Well, it's no different from if you are in base 256 and you write down 255, that's actually negative 1, right? So you could add a whole bunch of numbers and then you end up with a negative number. There's nothing weird about that at all in a finite field, right? When you're dealing with large real numbers, there actually is something kind of like that. The P-Adic numbers, where there are numbers represented as a large infinite string of digits that actually are a representation of a finite number, and often they're going to be negative, or there'll be negative fractions. Um, so, so now that we kind of got that understanding that this is going to happen, we have situations where if I expand only n times, that's what the tail looks like, and if you expand halfway, you're still going to get the same value for s. It's just that the tail will need to adjust, right? So if I expanded this to 1 plus 2 plus 3 plus 4, and the full n was actually 8, it just means that the finite sum for it is smaller, in this compensates. Now, if we say that the tail of s expanded n over 2 times, right? Instead of getting this, we get a tail that looks more like that. Just something to note, that the tail and the sum are actually related, and you can algebraically calculate it. You don't have to do any mental guessing at all. Okay, so currently there's not enough information to assign any particular value to s, right? So we will need to make use of other known values of sequences to figure it out. Since we never use the notion of infinity in this proof, we can't use arguments that have a dot plus 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 on the end of a sequence. That's something I want to hammer home a lot. There's something kind of wrong with it. It's like I know what you mean, but you didn't give me a procedure to calculate it. And there's a lot of checking guess type stuff that goes on, and it's not right, because you're trying to automate things in computers, and you're making things impossible when you do that. Okay, so we'll make use of a geometric sequence just to start off, to try and get something that'll help us to do the proof. So if we say that we have a number, and then we add numbers that are multiplied times some constant, say times 1/2. So if I say a equals 1 plus 1/2, it would be 1 plus 1/2 plus 1/4, 1/8, 1/16, blah blah blah. And you may know that when you do that, it actually will solve for a value of 2, right? And if you say a equals 1/2 plus x plus 1/2 a, you solve for value 1. In any case, this is a pretty general sequence. So if I subtract xa from both sides, I get a minus xa, and so I get this. And I divide by, and of course you can't divide by 0, so you can't plug in the value of 1 for x. That would be neat if we could, because it would give us an answer right away if we're allowed to, but we can't, because there'll be a divide by 0. So what we do is we know that this thing, we can plug in a value to get the final value that it should have, and we also can just literally take this statement seriously. If we take this 1 plus xa seriously, we say 1 plus x times this, and then we end up with 1 plus x to the 1 plus x squared, and then we notice that that 1 should be an x to the 0, and so then we notice that we've expanded all these terms out, and if we go to n terms, so we get the sum of everything from 0 to n, but we can't say plus dot dot dot. Instead, what we do is we figure out what the tail is. And for these kind of sequences, the tail is actually pretty easy. It's just basically like the next term times a. Because you can think of a as being, in parenthesis, it says x to the 0 plus x to the 1 plus x to the 2, dot, dot, dot. Right? And so this is the actual sum. Notice it doesn't say to infinity. I would I wouldn't write anything going sum from 0 to infinity unless I absolutely had no other way. This is a much better way, because everything becomes very concrete. So you have the sum, and then you have the tail, and if you notice, it's this last value here, x to the n plus 1 times a, which is this over here, right? And so if we have this value a, the reason why I created it is because I don't need increasing powers. What I really need is I need increasing integers. So I'm going to differentiate it. And if I differentiate it, I can differentiate a directly, and I get what I could plug in what the next value is going to be. But I could also take the sum plus a tail and differentiate that as well. So instead of x to the j, I get j times x to the j minus 1, right? And so it'll be 0x something, and the next term will be 1x something, and then 2x something. So that's something to start with. And also, just notice that if I differentiate this whole thing, I would end up differentiating the tail as well. And so, notice that because we're not dealing with infinite sequences, I have more flexibility in doing things with the summation without breaking anything. So our summation is finite. The first term is 0. So we can actually say that when we differentiate it, these two are equal, where I only start at term 1, right? Because term 1 is known to be 0 because it's times j. So now I have from 1 to n. I have this sequence, and I have this complicated tail. And you're like, what on earth is this for? It's so that as this increases, it causes the sequence as a whole to decrease, so that no matter how many times you expand it, f of x is always the same value for the same x. No matter what n is. You can keep increasing n. But basically what happens is you increase n, you put more stuff in the finite sum, and then this other stuff mops up the infinity on the other end. Okay, so if we have this f of x, and we evaluate it at minus 1, we have this term where it alternates between negative and positive, right? And of course, this is here so that it always comes out to the value of 1/4. And it's kind of wild if you write some Python code to do this, and you keep increasing n. This value keeps going up to give you the finite value, and this one basically squashes it down, so no matter what, it always ends up being the value 1/4. That's actually kind of surprising. In any case, yeah, it comes out 1 minus 2 plus 3 minus 4, etc. And the reason why we chose it is because it's pretty similar to the value s. The value s is 1 plus 2 plus 3 plus 4. And this is 1 minus 2 plus 3 minus 4. And the reason why we're going to do this is because if we subtract them, then we can make it so that only the if this is the first term, the second term, like the second term, the fourth term, sixth term, so these add and these cancel. And what that will do is it'll give you something that ends up looking like 0 plus 4 plus 0 plus 8 plus 0 plus 12, or 4 times 0 plus 1 plus 0 plus 2 plus 8. This, when I see proofs of negative 1/12 is equal to the sum of all integers, every proof I've ever seen just like skips over this as if it is self-evident. It is absolutely not self-evident. That's a step that I don't believe is actually sound. Just because in general I'm highly suspicious of infinite processes, because there's so many things that can go wrong because you're not being like absolutely concrete and like being able to go step for step where you can always break it down. There always seems to be some sort of logical leap where they didn't feel like it was worth writing down. But this whole thing of you can have an infinite sequence that alternates between zeros and increasing integers, I think that requires proof, because so many of the other sequences are strange. Even like adding a 0 to the beginning of a sequence, I think it's kind of dubious. You actually have to be able to do it in like a concrete way. But in any case, if we take s minus b, remember it's sum plus tail. So you have the sum of s minus the sum of b plus the tail of s minus the tail of b. And the whole trick to this is seeing if the tails come out to actually match. So if I put in the per term summation, so I literally put in sum of s, which is 1 plus 2 plus 3 plus 4. So this is going to be 1 plus 2 plus 3 plus 4 because it's this j term. But then I'm going to subtract the s term, which is it's because it's subtracted. The original 1 minus 2 plus 3 minus 4, the negative sign is flipped on it. But in any case, so it ends up being this per term sum when I represent sum s minus b, and also the tails. I'm going to be really, really, really super with the tails because I'm going to use the tails to figure out what the value of s is. So if I factor out the j, then and it's basically saying there's a j that is either multiplied times 2 or it's multiplied times 0. Right? So if it's -1 to the 0, it ends up being 1 plus 1, right? So using this, it'll alternate like this. It'll be like 0 plus 2 plus 0 plus 4. All right. Now, I was saying that I don't like the idea that you can just like skip all the zeros in between. So you have to be really careful and think about if you were to group pairs of this summation, then what you would have to do, I would have a summation for the 0 part, but it just dropped it because it's, it would be 2 times 0j for these j for j plus 1, right? But in this case, I'm keeping the terms that are positive. So it ends up being that you have 4 times that. And the reason why is because it ends up being even odd. So there's a times 2 in this direction, and then when it coincides, there's a times 2 in this direction. So it ends up being 2 times 2j. So this is really 4 times what you normally have in the sequence s, except it only adds half the values, and you have to be really, really, really careful with this step, because if you want to prove it just using plain algebra and you don't want to get into infinities, you have to be super, super careful. So what I'm saying is this it's sum of s. What do you do? Oh, there should be that needs to be n over 2. I didn't add them early enough. All right, but yes, let me fix that right now. So if I have s, the first place are s minus b, and you go up to n over 2, you have to be careful. You have to be careful. Yeah. So when you say 4 times sum of, I think that's it right there, n over 2. Yeah. I thought I proofread this. I didn't spend a whole lot of time proofreading, but yeah. So I'm being super, super careful. Okay, so because it only went up to n over 2, 4 times sum n over 2 for that and that. And what happens is I got here and I looked at this expression. I want to figure out what s is, so I'm going to guess that maybe this is 4 times tail s of n over 2, and I already figured out what that value was. And it's that in a simpler form. So it's 3n squared plus 6n over 24, or it could be 6n squared plus 12n over 24. So s minus that. So I'm making a guess that that's what the value is for that. That 4 times whatever, because if it is, then this would be 4 times s, right? Because it would be sum plus tail. So under the assumption that this thing, once I simplify it, will be equal to tail s n over 2, I'm going to try that out. So I say s 6n squared plus 12n over 48, right? Because I ended up multiplying it times 2 on top and bottom. It equal to, where I took this and I said, if this is 4 times the sum, then maybe I multiply times 4 and divide by 4. So I multiply times 4, divide by 4, and so this is what I have on the inside. So I'm really, really careful here, and I have an issue. N over 2 is an integer. That means that n must be even, right? So because n is even, then I can take this n here to be even. Got to be careful about that. Okay. So in that case, I get 6n squared plus 12n plus 3, right? And then if I split that out, this is minus this whole thing, so just be careful. This is 6n squared plus 12n over 48 minus 3/48. Interesting. That might help us figure out what s is, right? So I add in this on both sides to cancel it out, and I get s minus s over 4 is equal to 3/48. And then I subtract s over 4 from both sides, and so I get 3/4 s, right? Because this is 4/4 s, and remove 1/4 s, this is 3/4 s. And then if I divide both sides by 3 and multiply both sides times 4, wow, s equals negative 1/12. There's many ways of doing the proof. Most of the ways I've seen of doing the proof are extremely waffly, and I don't believe all the steps, but that doesn't mean that the fact isn't true. It just means that it's either irrelevant proof or it's close enough to help you to find the things that need to be patched up. In any case, often what happens is they take a different route and they play with things that have a dot plus 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 on the end, and they end up messing with the sequences, and they say, aha, and then they end up doing this step next. But what I did here is I calculated it by figuring out the sum plus the tail, and I had to have tail of s over n divided by 2 because I only expanded halfway out to deal with this whole zero thing. In most proofs, because they're using infinity, they'll just say that they don't even make the distinction between expanding twice as much or expanding half as much, and I think that's where the proofs actually are not correct. They need to be finite and doable without making any references to infinity. But in any case, once I have that s is equal to 1/12, right, and I have 4 sum s n over 2, 4 tail s n over 2, whether it doesn't matter what the value n is, if it's sum s of something plus tail s of the same thing, then that's equal to s, right? Because it's just like whether if you say I'm going to expand n values for this, and then there's going to be a tail to represent what the rest of it is, and if I expend 5 more values, the value comes out the same. It's just that the tails end up being altered to match it. So what we do is you do s minus b is equal to 4s, and if we subtract 4s from both sides, and then add b to it, then b moves to this side and negative 3s over this side, and b is actually just the value 1/4, which we already established otherwise. And so if we say s is equal to 1/4 divided by negative 3, and that's how we also get negative 1/12. Let me show you why that's 1/4. This is one of the things that makes doing things this concretely is like really wonderful. So I have a recursive equation, and I use the recursive equation to expand it like this, okay? But I started with a recursive equation, but I couldn't get like the linearly incrementing thing, so I did a differentiation here to make that actually work. And I have a different problem. It's like something that comes out the natural log of I'm gonna say it was natural log of 2, but I integrated what started off as an initial recursive sequence, and I came out with the same value for this infinite sum that, like, I have no idea how the person thought of the sum actually came up with it, but there's a pretty reliable method for doing lots of infinite sums. But in any case, you start off with a recursive equation, you differentiate it, on both sides, but on this case, I made the whole thing concrete, and I only have n terms expanded, not infinity, and then I have a tail afterwards. So I literally differentiated both of these, and also differentiated this. So if I plug in -1 to here, so 1 over 1 minus minus 1, that's 2. So 1 over 2 times 2, 1/4. So that's why b of -1 is equal to 1/4, and it also expands like this sequence. Right? That's like the whole main characteristics of this is you define these recursive equations so that you can first solve it for a value to figure out what the value is, and then you can expand it. And the fact that it's ridiculous is not a problem, because if you think it's ridiculous, you're imagining that you do an infinite number of iterations, and at the end of the infinite number of iterations, you encounter a wrong value, and of course, you can't encounter the wrong value because you can't iterate an infinite number of times. It just doesn't work that way. This is the first example, right? So, how many power 2's are you going to add before you're worried that you're going to get a -1? You're not. It's just that if you had a similar sequence, if this is one greater than this one, then it ends up being -1. So if I said that t is equal to 9 plus 10s, it would be an infinite number of 9's. So the number 9, infinite number of times. What it's really saying is if you were to add 1 to it, the value becomes 0. And that's why it's called -1. And it literally is -1 because of that reason. And this also works with sequences that converge. The other thing that people on our internet argue about, where they argue over is 1 equal to 0.999999. Well, there is no tiny value that you have to add to it, because you can write it down as you can say v is equal to 0.9 plus 0.1 v, and you can solve that for the value of 1, and you can also expand it for 0.99999 going on infinitely, right? And that's I don't understand why people are not using recursion for this. It's far superior. But in any case, this is the -1/12 equals 1 plus 2 plus 3 plus 4 blah 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 proof. It is true. It's kind of related to P-Adic numbers, but this is actually more complicated than P-Adic numbers. P-Adic numbers are basically a system where you not only have an infinite number of digits that go to the right of the decimal point, but you can also have an infinite number that go to the left of it. And of course, it's not as weird as it sounds, because when you say that like this sum is infinite, what are you talking about? Well, this sum is infinite, but the tail is also negative infinite. And that's why this can be -1/12. This can be the sum of every integer, and this is a tail that cancels it out, right? So what you're saying is when the sum is not actually s. The sum is finite. This is telling you something about infinite numbers that maybe you don't already know. That they don't really like physically exist in like a sense that you certainly can't do an infinite number of iterations. So what ends up happening is you get forced to where if you want to know the value of a sum, then you take s minus tail, and something really beautiful happens when you do that. In this case, I can do this just like a real quick. This will be the last thing I do. So if I say -1 is equal to 1 plus 2s, then once I've expanded it out, and I know that it's going to be 2 to the 0 plus dots up to 2 to the n plus 2 to the n plus 1, and if you end up doing this on your own accidentally, you're gonna totally like believe this system after you see this. Okay, and so s minus tail will give you the finite formula for the sum. So if I were to add 2 to the n plus 1, right? So it was minus that value, and so if I add it to cancel it out over here, then it literally gives you the formula to calculate. So really, this is the sum. So the sum of all the powers of 2 from 0 to n is 2 to the n plus 1 minus 1. And what that means is you can just do this in your head. You can say 1 plus 2 plus 4 plus 8 minus 16, right? So that's literally the formula that gives you minus 1. Well, you can flip that around. You can say, what's the sum of all powers of the first, like, say, 5 powers of 2? It would be 2 to the 6 minus 1. You know, what's the sum of all for the 8, you know, from 2 to 0 to 2 to 8, all added together? Well, it's 2 to the 9 minus 1. It's a general phenomenon. You can so if you know S and you know the tail, then you can literally calculate S minus tail is equal to sum, and it'll give you a closed form sum. But anyways, that's it. Figure out how to turn this off now.